Okay, so we're going to talk about limits involving infinity. And so everything that we've had so far, our x's have gone to some real number, or goes to some real number, and then we get some real number out of this. Occasionally, though, we'll either try and go as x goes to infinity, or we're going to find that we get a limit that goes to infinity. And so I want to discuss where those things come up, and you've already seen actually most of them. Okay, so remember from the pre-calculus section in the last few weeks, we were talking about long-term and short-term behavior, and we had expressions where x will go to infinity for the long-term behavior, or f at x goes to infinity if we have asymptotes and things of that sort. And so this is really an exercise in notation more than anything else. The concepts we've already dealt with. So let's look at one of our toolkit functions. So we have f at x equals 1 over x. And so the way we would notate the short-term behavior, or the long-term behavior, excuse me, as x goes to infinity, 1 over x goes to 0. So what we had used, kind of that double arrow before of saying something like, as x goes to infinity, then f at x goes to 0. Now we have a little bit more precise notation that says our limit as x goes to infinity is 0. So hopefully this is just more a translation of notation than any new concept here. And then if we look at the short-term, the long-term behavior going the other direction, as x goes to negative infinity, 1 over x also goes to 0. And you can see that from the left side of the graph. Now for short-term behavior, we can use the notation as x goes to 0 from the left side, from the negative side, 1 over x goes to negative infinity. And the companion to that is as x goes to 0 from the positive side, 1 over x goes to infinity. And so the overall limit as x goes to 0 doesn't exist because those two values don't equal each other. One's infinity, the other one's negative infinity. If we had the function g at x equals 1 over x squared, now here, since the short-term behavior both from the left and the right both go to infinity, then it's fair for us to say as x goes to 0, 1 over x squared goes to infinity. In this case, since this is negative infinity and infinity, that limit does not exist. And of course, the other limits are the same as they are with the previous one. As x goes to infinity, 1 over x squared goes to 0. And as x goes to negative infinity, 1 over x squared goes to 0 as well. And so with those 7 limit statements, we describe the short and the long-term behavior of these two toolkit functions. Okay, so it's just a matter of notation at this point. So remember, infinity isn't a number. It's really a concept of x, or f at x, increasing or decreasing without bound. And so it's just a shorthand that says that as x goes to 0, 1 over x increases without bound. All right? So make sure we're not making infinity a number. It's the idea that the value of this thing is increasing forever. Okay, so these two things here, where we have 1 over x as x goes to infinity or negative infinity, going to 0, these are going to be tools for finding general limits that we're going to find for the next couple slides. And so when we have ratios of polynomials and things of that sort, sometimes we'll get 0 over 0. This gives us another tool for removing that concept of 0 over 0 or infinity over infinity. And so here I want to use limits to describe asymptote behavior. Remember how we did that? Basically, if we have this function where we have x plus 1 times x minus 2 over x minus 1 times x plus 2, we know we have the asymptotes of x equals 1 and x equals negative 2 and y equals 1. We know that from just picking this out, that we have discontinuities where x can't be 1 or negative 2, and that we also have long-term behavior since the degree of the polynomial in the numerator and the denominators are equal, so the ratio of the leading coefficients will be 1. And so basically what we say then is the limit as x goes to infinity of f at x equals 1, the limit as x goes to 1 from the positive side is negative infinity. As it goes to 1 from the negative side, it's infinity, and then as the limit as x goes to negative 2 from the positive side is negative infinity, and we have the last one as we go to negative 2 from the negative side, that goes to infinity. And so then the long-term behavior, and we get our graph. So there's the process is exactly the same that we've used before, where we're anticipating what happens as x goes to infinity or what happens to f at x. Sometimes that goes to infinity with your vertical asymptotes. We just have a different way of notating it now. And so this is the notation I'd like you to use when we're back examining these kinds of functions. Now the way we'll find these is you can do it just the way that we did before, where we look at certain intervals and find, x plus 1 as x is greater than negative 1 is always positive, and we go through that kind of analysis. But the statement of these things now can be written as limits. Okay, so let's remember that as x goes to infinity, 1 over x equals 0. And in general, anytime we have x to the nth, 1 over x to the nth, that also, the limit of that also goes to 0. And that comes from that property. Remember that when we have a limit going to a value, if we take it to an exponent, we'll have that limit value to an exponent. So we have 0 to the nth power, which remains 0. Okay, so let's look at this one here. I want to evaluate this limit as x goes to infinity. And so this is pretty hard if you think about it. You can put in a really, really, really big number, and then you're doing a lot of computation, and you're not quite sure if you're close enough to the limit or not to make a guess. And so there's a little bit more sophisticated way to do it. What we're going to do is we're going to multiply the numerator and the denominator by 1 over x to the highest degree. So this is a second degree polynomial, and this is a second degree polynomial. So I'm going to multiply this times 1 over x squared, both numerator and the denominator. And so what I get here is when I distribute this thing, notice I get 3 plus 2 over x minus 1 over x squared as this gets distributed in the numerator. You see we have 3x squared times 1 over x squared just as 3. Same thing in the denominator. I have x squared times 1 over x squared is 1, and then minus x times 1 over x squared. Notice I will have then a negative 1 over x. And then 5 times 1 over x squared is just, actually this should be a positive, I think. Like that. Okay, so then we know what the limits as x goes to infinity is now of all those 6 terms, right? The limit as x goes to infinity of 3 is just 3. Of 2 over x now is going to be 0. And minus 1 over x squared as x goes to infinity is going to be 0. So we're going to end up with this real nice ratio of 3 over 1 equals 3. So the rule of thumb that we've had before remember, was that when the degree is the same, the long-term behavior of this polynomial is going to be the ratio of the coefficients. Now we've done it analytically. Okay, so we've shown where this comes from, with the fact that this simplifies, or not simplifies, but it transforms into this expression, which we know from our limit laws what happens to the expression when x is in the denominator. We just get 3 over 1, which equals 3. So this is the more formal way of arriving at the leading coefficients. The ratio of the leading coefficients is what your long-term limit is. Okay, so you try these. Same kind of thing where do this, I guess, yeah, just try them like this. So the first one, we're going to go to -3 from the positive side, and then the next one we're going to go to infinity. You factor the denominator to x plus 3 and x minus 3, and so you'll see that we have asymptotes at 3 and -3, and since we're looking at the short-term behavior of -3, if we come from the positive side, what do we have? Okay, so let's look at these terms individually here, where we have 2x squared plus 1, and then we have x minus 3 and x plus 3. So this thing, when it's the numerator, when it equals -3, that's going to be a non-zero number. And the denominator is actually going to be 0. So we have something divided by 0 that's not 0 divided by 0. So we're going to have an asymptote that, or we're going to have a limiting value that it's going to go either to negative or positive infinity. And so we can decide which way it is, that when we look at it from the positive side, we're going to be a little greater than -3. So this is a little greater than -3, so this would be like -2.9, right? This is going to be negative, and then this is going to be positive, right? So we have a positive number here. This one is going to be negative, and we know this one's going to be positive, and so that's where we get the, this should be, I think I have it backwards, right? If we come from the positive side, we should be a little bit less than, yeah, this is actually negative infinity. Okay, so then the second one, when we go to infinity, we're going to have infinity over infinity. So let's see what happens here if we use the technique that I was just talking about, where we're going to multiply both the numerator and the denominator by 1 over x squared. And so what we get is an equivalent expression that says 2 plus 1 over x squared and 1 minus 9 over x squared. And so as x goes to infinity, these two terms are going to go to 0, so we just have 2 over 1, and so we have 2. And so that's going to be our horizontal asymptote. Oops, sorry. So it's the same thing that we were doing before. We're just using now limits to demonstrate it a little bit more formally. Okay, so that's limits. Now what I want to do is talk about derivatives and rates of change again. And we're going to revisit this notion of a tangent and a secant line and end up with our limit expression. So let's say I have this function, And I'm interested at what happens to the function at a. All right, so at any other value x, I have this value f at x. But I'm interested in what is my rate of change at a. And so the way I'm going to do this is if I take two different points along this curve, if I take f at x minus f at a and divide it by x minus a, I'm going to have the slope of this line, right? These are just 2 points and I'm calculating the slope. So that's going to represent my average rate of change between the 2 points. Now, if I make this difference, this a to h, I'm going to call a to x, I'm going to call this h. I'm going to call this difference h. And so then f at x now becomes f at a plus h. So if I take a plus h, then I get to x. Okay, so I'm just going to make a substitution here of, instead of writing x, I'm going to write a plus h. And then if I have a plus h minus a, I just have h. And so here I have this expression. It's still the average rate of change. So I can get to my instantaneous rate of change at a, and I'm going to call this now the derivative. It's as x goes to 0, what happens is I'm going to make this line, imagine this point here, getting closer and closer to a, and what happens to my tangent, what happens to that secant line is it becomes a tangent, and so this represents, the slope of this represents the instantaneous rate of change at a. And so here we have this form where, and I'm going to call this f prime, and I'll get into some terminology, or I'll get into some notation in a little bit. But for now, just look at this as the instantaneous rate of change is this limit as h goes to 0 of the function evaluated at a plus h minus the function evaluated at a divided by h. And so hopefully you'll recognize that a lot of the limits that you were doing had something like this, where we had two functions, the difference between two similar functions, but perhaps the first one had a little extra to it, divided by some other difference or some singular value. And so here's where we get into this. As h goes to 0, we're going to have, f at a plus h is going to equal f at a, so we're going to have 0 over 0. And this is why we get into those limits of 0 over 0, and how we're going to deal with them will be how we calculate derivatives and these by using these limit properties. Okay. So what I want to do now is I want to calculate the rate of change at 1, given that my function is x squared. So if I look at what this means graphically, x squared looks like this. Okay, and I know when x equals 1, f at x equals 1, right? And I want to know what's my rate of change here. So in other words, what's the slope of the tangent line that's along there? Okay, so I'm going to set this up using that definition that I had before, that limit definition. I'm going to say it's going to be the limit as h goes to 0 at f at 1 plus h minus f at 1 divided by h. Okay, so here I'm applying that instantaneous formula. Actually, I'll write this up just so you can refer to it. H goes to 0. Okay, so there's my definition there. Or I can take any, we're talking about individual values, so I'm going to make this just some number c. And in this first example, c is going to be equal to 1. All right, so what I have to do now is make the substitution where I'm going to find the limit as h goes to 0. I'll plug in 1 plus h to my function, which is just x squared, minus 1 squared over h. And so what I'll do is then expand that. So I get 1 squared plus 2h plus h squared minus 1. And I apologize again for my small writing here. It's kind of hard to fit all these things on without, making a bunch of charts and losing track of where we've been. So I'll simplify it here. And I get 2h plus h squared over h. And then if I factor out an h, I can cancel the h's, and I get the limit as h goes to 0 of 2 plus h. And this one's easy. It's going to be 2. So the slope of this line that's tangent at this point is 2. How many of you have taken calculus in high school or before? Okay, this is going to be frustrating for you especially because we're going to be calculating derivatives with limit laws before we get to the rules of differentiation. And you probably remember the rules of differentiation more so than the limit laws to get to differentiation, right? So this all of a sudden will become so utterly easy with the rules, but it's important to learn it with the limit definition. In fact, this is going to be the first question on your final exam is, define a derivative using limits. I'm going to tell you what the first question is. So it's a concept that you have to know for this class. We want you to know it. And so if you already know the rules of differentiation, it's going to take a lot of concentration to ignore them because hopefully all of you will see with a matter of relief what the rules are. Something like x squared differentiates very, very quickly into just 2x, okay? All right, so let me give you another example here. This is with, the first example that I had was with a value. And so it gives me the particular tangent. But let me do it by calculating the function, okay? So that at any point I know what the function is. So I already know this, that the derivative at 1 is 2 and that f at 1 equals 1. But let me lay this out. I'm a little bit ahead of myself. What this slide is really about is I want to know what the equation of the line is now given the tangent, okay? So here I have my tangent. I want to know what the equation to this line is. And the reason why we would want to know the equation of the line is sometimes functions are really hard to calculate, and computers can calculate linear equations very, very fast. And so we often will approximate functions with a linear equivalent by using the tangent line. Okay, so here what I want to do is I know that this point is 1, 1, and I know what my slope is, which is the tangent. And so I'm going to use the point slope form to, I'm just rewriting the point slope form to make x1 is my value a, f prime at a is my slope, and f at a is the value of y for that first point. And so I have, if I plug in the values that I have, I'll get y minus 1 equals 2 times x minus 1. And so my equation then becomes y equals 2x minus 1. And so that's the equation of the line that's tangent to x squared at x equals 1. So very, very close to 1. These two things are very, very close to each other. And so this is a useful exercise because this will allow us to estimate values that are close to 1 without having to calculate the more complicated function. Okay, everybody follow this? I'm sorry, I went down to down the road on the next subject before I really adequately explained this. But
Why is the tangent line y equals 2x plus 1 when you got y equals 2x minus 1?
It should be minus 1. I think I have a... Oops, no, what I want to do is... Okay, there it is. Good catch. And you know it's going to be minus 1 because look at where the intercept is. It's down at -1. Okay, and in fact, last time I talked about it, I made that correction. Okay. So I want you to try this now. I want you to find, and this will probably close out today. It's about 4 minutes till the hour. So I want you to find the equation of the tangent line to f at x equals the square root of x at x equals 1. So there's two things we have to do here. First, we have to find the slope of this using the limit laws, and then we'll find the tangent of it. So first we'll find the derivative, and then we'll find the equation of the tangent line. Okay, so go ahead and try this. Set up the derivative by using the this definition, and so this is going to be the limit as h goes to 0 of, since our function is the square root of x, this is going to be x plus h minus the square root of x over h. And so that's going to give you the slope of that line.